we have a lecture class, okay, quite early, okay, at 9 a.m. Okay, I see maybe some of you are not fully wake up. Okay, you try to follow my lecture here. Okay, I will continue with chapter 3. I haven't finished chapter 3, which is about the logic to CMOS. Okay, now I will share my screen here. Okay, for this chapter 3, okay, I have a cover about how to draw the schematic diagram, okay, based on the Boolean functions given, and then with the schematic diagram, and then how to draw the stick diagram. Okay, so today I will continue with the stick diagram. Okay, there are a few more examples here in the lecture notes, okay, that shows how to draw the stick diagram. Okay, so in the previous class, the very fundamental steps to draw the stick diagram is already shown to you. Okay, so there is not difficult. Okay, they are not difficult after you understand it. Okay, so now I will continue with these examples. This example is also about drawing the stick diagram. Okay, just that this stick diagram, the order of the polysilicon gate is random. Okay, it's random. We can actually properly arrange the order of the silicon gate. Okay, but we have to use a method. Okay, the method that we usually call it is ULIF path. Okay, ULIF path. Okay, later I will cover that. Okay, what is it about ULIF path? Okay, you will learn this today. So this is important because you will need to apply this method. Okay, when you want to draw your stick diagram, and then based on the stick diagram, you also can use it to draw your layout if the circuit is complicated. Okay, okay, so now I will start with this example. Okay, these examples, as you see that there is a Boolean functions given, z equals to a, and with the d, and all with the e. Okay, and then this one, let me see. Okay. Okay, this is n or and n. Okay, this Boolean functions, this is for the PMOS. Okay, we can also write another functions here to represent it for the NMOS. Okay, PMOS and NMOS here, it is actually the pull up network and then the pull down network. This is pull down. Okay, so for the functions of the pull down, so it is Z bar equals to A Okay, so now we can see what is the configurations of the PMOS and NMOS in pull up and pull down network respectively. Okay, for this one, as you see that the schematic diagram has already drawn here. Okay, if you want to do the practice, you can try to draw it yourself without referring to this diagram. Okay, after you draw it yourself, then only you'll refer to this diagram to see whether it is correct or not. Okay, to check, then we see this function. Okay, since the B and C. Okay, I will look at B and C. Okay, we also can look at this term A, N with the E and O with the E. We also can look at this. Okay, but if you want to look at the simpler, the term that is more simple one, okay, this is the simple one only with two transistor. So we can look at this as well. Okay, we can look at this first and then we see this one. Okay, and B and C, this is an AND operations. So AND operations, it means that it is in series. Okay, AND operation is in series in pull down network. Okay, so this is the series configurations for the transistors that are having an input of B and C. Okay, and then this is AND operation as well. This is series. This is parallel. So you can see that D and E, they are in parallel and in series with A, transistor with input A. Okay, so this is the pull down network. And then for pull up network, okay, pull up network is opposite configurations than the pull down network. Okay, so when the B and C is in series, means that they are in parallel. Okay, so in pull up network, B and C is in parallel. Okay, and for others configurations, the transistor D and E here is in series. Okay, and then it will be in parallel with the transistor. Okay, with this transistor with input A. Okay, initially they are in series in pull down network, but in pull up network they are in parallel. Okay, you see the difference, right? Okay, so this is how you should draw the diagram. This is the schematic diagram. Okay, after you draw this, then you can start to draw the stick diagram. Okay, here given a stick diagram, which is a bit different than the ones that I showed you previously. Okay, it look like this. This is also a stick diagram. We call it stick diagram. Okay, this stick diagram is with random ordering of polysilicon gate. Okay, means that the order of the polysilicon here, this is the polysilicon. Okay, the gates for all the transistors. Okay, they are in random ordering. It's not proper arranged. Okay, we can have a different orders of polysilicon gates. Okay, different orders of polysilicon gate means that we will have different connections. Okay, for each of the transistor that is connected to the VDD, ground, and output. Okay, so for this one, the polysilicon order is A, E, B, D, and E. Okay, and then the connections here is drawn in this way. Okay, okay, to understand this stick diagram, it is a bit um, confusing, okay, it will take times, okay, for you to understand what is means by the connections here, okay, but it can be understand based on the schematic diagram that is given here, okay, but then it will take time for you to understand this, okay, because the connections here is a bit complicated, okay. Okay, for A and B here, okay, this one, let's have a look on the connections here, okay. Uh, okay, as from what I remember, this stick diagram, the connections here is actually not consistent with this stick diagram. Sorry, with this schematic diagram. This schematic diagram is correct. Okay, just that it does not really reflect the connections that is drawn in this stick diagram. Okay, why I say so? Because you see that A and B transistors, okay, these two transistors, okay, they are having a source terminals that is connected to VDD. Okay, and if we want to check back to this schematic diagram, you see that A and B here, A and E, the source terminal is actually not connected to the VDD. Okay, this is source and drain, source and drain. Okay, so E is actually not connected to the VDD. We can actually rearrange the transistors here in the schematic diagram to make it consistent with this stick diagram. Okay, so you will have to redraw another stick diagram, the similar one with this one, just that with different arrangements of the transistors here. Okay, so when we draw, then this schematic diagram should look like this. Okay, so I draw the pull up network first. Okay, this one pull down network. I will not draw it. Okay. Later if need it, then I will draw it. Okay, for now I will draw the pull up network first. Okay, so for this one, the A and E, okay, transistor. Okay, now the source terminal is connected to VDD. Where's my cursor? I cannot see it. Okay, this is source. This is source. Drain. Source. No, this one is drain. Source and drain. Okay, so source terminals for the transistors. This transistor and this transistor is connected to VDD. So it means that these connections here. Okay, I draw here, I highlight here. Okay, this is the connections that I mentioned now. Okay, and then drain of this transistor A is connected to the source terminals of B and D. Okay, so we can see this drain terminals of the transistor with input A is connected to the drain. Let me see, is it drain? Not drain, this is source. Okay, the drain is connected to the Okay, I finish label this first. Source, drain, source, drain. So this is B and C. B and C, the source, both of these source are connected to the drain terminals of A. Okay, so I'm looking here now. Okay, this part, the connections here. Okay, and the connections here. Okay, you see this drain terminal of the transistor A now is connected to the source terminals of A and D and also C. Okay, here you see this one. This is source terminals of B and C. Okay, and this is the drain terminal of A. Okay, but this one is drain terminal, it's not source terminal. Okay, it should be a drain terminal, okay, not source terminal. Okay, so you see this, the connections can make us confused easily. Okay, this stick diagram that is with random ordering. So we actually not encouraged to just simply arrange the polysilicon order. Okay, and then just now I show you, then you know. Okay, now you know uh, why this is uh, um, not a good one, not a good stick diagram to show. Okay, because of the connections here is actually quite confusing. And then another one is the area here. Okay, this is the con not okay, let me highlight this first. Okay, okay, the one that I want to show you is the area here. Okay, this is called as the diffusions area. Okay, so this diffusions area, this is the P diffusion area. This is N diffusions area. Okay, in previous stick diagram that I showed to you, okay, the diffusions area is only show using a line. Okay, in this stick diagram, the area of the diffusions area are drawn. Okay, uh, so if you draw in this way, it is also accepted. Okay, just that the order of the polysilicon, you will have to arrange it properly. Okay, and make the and draw the correct connections here. Okay, so this one I will not show you all the connections. I would just want to tell you what are the difference here. Okay, the stick diagram with with random order of the polysilicon gate and then with the proper orders of the silicon gate. Okay, later there is another stick diagram also show in a similar way, but in proper ordering of the polysilicon gate. Random ordering may increase the area due to separations of diffusions area and complicated routing signals. Okay, so these tools are the drawbacks. Okay, are the situations, okay, that will be encountered if we randomly or draw the order of the polysilicon. Okay, to proper ordering the polysilicon, um, there is one method, Euler path. Okay, if do not proper order the polysilicon line, the numbers of diffusions breaks may increase. The separations between polyline may be large. The overall horizontally dimensions may increase. Okay, this means that the diffusion area um, will break. Okay, the numbers of the diffusion area will break. This is the meaning if you refers to the drawing here. Okay, so you see this, the breaks here refer to this break. Okay, suppose they are connected. All these diffusions area, they can be made connected. Means we can just draw a large area to represent it as the diffusions area. Okay, but in this stick diagram, they draw in this way, and then in between we call that this is a break. Okay, so the numbers of the diffusion breaks will increase, and then the routing signals will be complicated. This is the routing signal. Okay, this is contact, and with the routing signal. Okay, we also call it interconnect. Okay, this is the metal layer. Okay, the numbers of diffusion breaks can be reduced, okay, by proper ordering the polysilicon line based on U-leaf path. Okay, what is U-leaf path? Then I will show you in the next example. Okay, and before the examples, here are the definitions for the U-leaf path method. Okay, the U-leaf path approach is a simple method for finding the optimum gate ordering in the stick diagram. Find a U-leaf path in the pull-down graph and U-leaf path in the pull-up graph with identical orderings of input labels. The U-leaf path is defined as an uninterrupted path that traverses each branch of the graph exactly once. Okay, so the meaning of this I will show you through drawing in the next example. Okay, so U-leaf path here, sometimes we call it a U-leaf graph. Okay, U-leaf graph method. Okay, even though it is called as graph, but it doesn't look like a graph. Okay, it doesn't look like a graph. Instead, it consists of the path that is across each of the transistors. Okay, with nodes. Okay, later you will see that. Okay, so this is the examples. This example is the same one with the examples that I have shown you just now. Okay, and then this is the U-leaf graph method. Okay, that draw out with the U-leaf path. Okay, we call this as the U-leaf graph. Okay, the U-leaf graph techniques can be used to determine if any complex CMOS gate can be physically laid out in an optimum fashion. Okay, start with either NMOS or PMOS tree and connect lines for transistors segments, labeling devices with vertex point as circuit nodes. Okay, the nodes here is actually this node. Okay, you see there is a dot here. This is the nodes. Okay, this is the nodes. Okay, next place a new vertex within each confined area on the pull-down graph and connect neighboring vertices with new lines, making sure to cross each edge of the pull-down tree only once. Okay, the new graph represents the pull-out tree and is the dual of the pull-down tree. Okay, what is that mean is you can refer to this U-leaf graph. Okay, this U-leaf graph, they are actually two graph. Okay, there are two graph here. Okay, one graph is for the pull-up network. one graph is for the pull down network. Okay, and each of the graph here, they are with nodes. Okay, so this one is node, this one also node. Okay, the nodes here means the path from one node to another node, means that the path that is flowing from this node across one transistor to another node. Okay, later, okay, after I finish this, there is one more statement here. Okay, I will show you what is that mean, what is this Belief graph means, okay, with relate to this diagram. Okay, the stick diagram of this at the left side mean this one. It gives a very non-optimum layout for the CMOS gate above. Okay, this is the stick diagram. That is with random ordering of the polysilicon line. Okay, so now I will show you how to redraw this stick diagram. Okay, by drawing the Belief path in the graph. Okay, the Belief path, the Belief path for this schematic diagram has already drawn here. Okay, how to get this, I will show you now. Okay, first, we need to use this schematic diagram to determine where should we start to draw the Belief path. Okay, I will start with the pull-up network first. Okay, and then only I will then only I will draw for the pull-down network. Okay, in pull-up network, okay, before we start to draw the Belief path, okay, we need to determine the nodes. Okay, the nodes here is actually this one, this node. Okay, this node. Okay, so these are the nodes. Okay, and then to start to draw the path, we need to make sure that the path that is drawn is only draw in one direction, cannot reverse. Okay, we cannot reverse and draw the path. Okay, we only can draw it one directions. Okay, so for this one, if we want to draw it in one directions, we can start at this node. Okay, okay, we start at this node. Okay, if we want to start at this node, it's also fine, but you have to try, because if you start at this node, you may not get a path that can transfer only each through the transistor. Okay, so okay, if I start at this point, okay, you can see I start here and I go back here, and then I need to go back to this transistor A in order to B and C. Okay, so at this point, we cannot start here. We cannot start at this point, because if we start here, we go through the transistor with input A and then go back to this E and D. Then E and D, we want to go back to this, we want to go to pass through the transistor with input B and C. So we need to reverse back in this way, or in other way. Okay, this is not what we want, so we have to start at other point. Okay, so this one cannot. Okay, this point we cannot start at this point. Okay, we start at this point. Okay, so at this point, first we can pass through the transistor with input A, and then we pass through the transistor with input D and E, and then come back to this node. Okay, they are not overlapping, only one directions. Okay, so at this point, then we can pass through the transistor with input B, and then go back to this point. Okay, I will draw the directions here, then you will see it clearly. Okay, only it looks like this. This is the nodes. Okay, this is B, this is C, E, D, and A. This is called as the Uliffe path graph. Okay, for pull down network. Okay, and the path here we need to state as this: A, D, E, B, C. Okay, this means that the path start with the transistor with input A and D, E, B, and C. This is the directions of the path. Okay, I want you to write this down after you draw the Uliffe path, because you will be able to identify easily, okay, the directions of the Uliffe path for the pull down network. Okay, for the pull down network. Now we are drawing for the pull out network. This is the pull out network, not pull down network. Okay, this is pull out network. Okay, now we want to draw the Uliffe path graph for the pull down network. For pull down network, then we have to follow the same Uliffe path directions, mean this one. Okay, we have to follow, okay, the Uliffe path directions across each of the transistors must be the same in the pull up network. Both must be the same. Okay, so that we can draw the stick diagram here with the same order of the polysilicon line. Okay, so if I follow this one, I follow A. Okay, notes already draw here. So now start with A. So it should start from here. Okay, and then D and E. Okay, now there is a problem here. Okay, if we use A, if we start with A, D, and E, the problem here is it will go back to this node and then there's nowhere to go. Okay, that means that this Uliffe path cannot be used. Cannot be used. Okay, we have to find another way, another path, okay, that can use in both pull out and pull down network. Okay, so then this one have to do again. Okay, we have to determine another path. Okay, so this one cannot. This is not able to draw in the pull down network. So this one we cannot take it as the Uliffe path. We need to choose another one. Okay, to ensure that the path that select can be used in the pull down network, I will see this first. Okay, I see that we can start from E, D, A, B, C. Okay, and then here in pull-up network, E, D, A, then go back to C. Okay, so we can choose another one, which is E, D, A, E, D, A, B, C. Okay, I will check again. This one, E, D, A, B, C. Okay, so this one can be used. Okay, because these path directions um, can be used in both a pull up and pull down network. Okay, I will see the network, not network, I will see the stick diagram given here. Okay, see any other path that can be used. Okay, so given here is EDABC. Okay, so it's the same one. This is EDABC. It's the same one that I show you here. Okay, this is the same ULIF path. Okay, so the directions here, okay, it starts from here, this point. Okay, and then the directions here. Okay, so you see the directions of the ULIP path in a pull-up network, and pull-down network, it will be like this. Okay, start from here, this node. Okay, and then the directions will be like this. Okay, so when we draw, this is the shape of the path. Okay, this is the shape of the path. Okay, we draw it like just now what I have shown you. Okay, like this. And then you also need to draw a node. This is D, E, A. This is B, C. Okay, the directions is like this. Okay, this is for the pull up network. And for pull down network, this is pull down network. It look like it is like this. This is the node. Okay, remember that when we draw like this, we need to make sure that the nodes here are drawn properly. Okay, there is a node here. This is E and D. This is D, E, and A. Okay, there is a node here also. A, B, C. Okay, the node here, okay, is actually this node, the green color nodes. Okay, this one, there is a node. Okay, this node is the common node, okay, for the transistor D, E, and C that are connected to the ground. So this is the common node. Okay, so these two graph is the unit path graph for the pull up and pull down network. Okay, the unit path here already show. Okay, it is draw out here. Okay, this is the same one as what I have drawn here. Okay, so now you already know how to get this. Okay, so if you want to get a proper order of the polysilicon line, you have to use the unit path to get the order of the polysilicon line. Get a proper one, a proper order. Okay, after we draw this UD path, then we can start to draw the stick diagram. Okay, and this slide, okay, this slide show you the directions of the UD path, okay, based on the UD path that obtained from this diagram. Okay, now the stick diagram here is drawn. Okay, you see that with the proper order of the polysilicon line E, D, A, B, C, the connections here are more simplified. Okay, and then with no break of the diffusion area, we can see it easily here. The connections, which one is connected to VDD and which one is connected to ground. Okay, to compare this stick diagram to the schematic diagram, then we have to label the source and drain terminal. Okay, we can identify the connections to the source and terminal in each of the transistor. Okay, so for this one, okay, if we refer back to the schematic diagram, this is the schematic diagram that we should label. Okay, AD, this is a source, drain, source, and drain. This is drain, source. Okay, in these connections, okay, remember there is a node. Okay, this line is not just only one terminal. Okay, this line is actually connected with two transistors. So one here, the terminal is the source terminal. Another one is the drain terminal. Okay, and then this one is the source. Okay, so now I refer back to the stick diagram. I will look at these connections first. Source terminal. This is the source terminals of the transistor with input D and A. Okay, and then these terminals are connected to the VDD. Okay, so means that this is the connections. The connections just now is for these connections. Okay, that is connected to VDD. And then you see that the drain terminals is connected to the source terminals of the transistor with input E. Okay, they are in series. Okay, so you can see that this source, this drain and source, these two terminals are connected. Okay, they are in series. D and E is in series. And then this D is connected to the drain terminals of A and B, okay, and also C. Okay, these connections here represent this one. Drain terminal of A connected to the source terminal of B and C and E. Okay. Okay. So I think this is correct. This is D, and source terminal. Okay, here also source terminal, and this is drain. Okay, so correct. The connections here is correct. And then here the drain terminals for the transistors with input B and C. These two terminals are connected to the output. Okay, so this is the connections here. Okay, these connections is connected from the drain terminals to the output. Okay, so same for the pull-down network, also similar. All these connections we can identify through the schematic diagram. So you can compare. This stick diagram can actually help us to easily identify the connections, okay, with a proper ordering of the polysilicon. Okay, we call this stick diagram as the optimized stick diagram. Okay, there is another example. Okay, this example also, we need to use the ULI path to get the optimized stick diagram. Okay, and then the schematic diagram here, as you see that there is only 3 transistors. Okay, so this schematic diagram, we can easily find out the ULI path. Okay, so for this one, okay, we can start with the nodes here. Okay, we start here, we will get A, B, C. Okay, and then in pull-down network, we also can start from A. Okay, if we want to start from A, then we need to start from this node. Okay, so from this node, it will be like this. A, B, C. Okay, so the ULI path that is valid is A, B, C. Or we can get another one, which is C, B, A. Okay, in this pull up network, CBA is valid. Okay, in pull down network, CBA is also valid. Okay, what I mean valid here is the path must pass through each of the transistor in only one direction, cannot reverse, cannot overlap. Okay, another ULI path is B, A, C. Okay, means from B goes to A and C. Okay, for the pull down network, B, A, C. Okay, so ULI path is not just one ULI path, can be multiple. Okay, but you only have to select one in order to draw the stick diagram. Okay, so for this schematic diagram, you can identify 3 ULI paths. Okay, these 3 ULI paths can use to draw the graph. Okay, so for this one, the ULI graph, as you see, they are identical. Okay, this one is actually for the pull down network. The line that is with green color, so you see that they are similar. Okay, remember again, the unit path that is draw must be with the nodes. Okay, you need to draw the nodes as well. Okay, and then for the unit graph of the pull up network, okay, this one is the unit graph for pull up network in yellow color. The line is in yellow. Okay, so it is similar to the ones that I draw here. Okay, and okay, so this node, you see that the nodes here is labeled with I and J. Okay, so for this node, J is actually at this node already mentioned. Okay, already given here, J. Okay, so this is B, A, and then this is VDD. VDD is actually this node. Okay, and X here, X node mean this node. Okay, the output node. Okay, so this is the graph that we should draw right after we identified the path. Okay, so this is another examples. Okay, I see that we are almost time to break. Okay, we are going to take a break. Okay, but before we take a break, I want to add something on these examples. Okay, these examples that does not show the stick diagram. Okay, the the stick diagram, when you draw it, okay, you can use either one of all of these ULI path. Okay, if you use different order of the ULI path, that also means that your connections will be different. Okay, so for any questions like this that is with more than one ULI path, okay, as long as the ULI path that you get is in only one directions in through each of the transistor, it will consider correct. So if your ULI path is different with different order of the polysilicon line, then that they can consider to be correct. Okay, you just need to make sure that the connections that you draw is correct and according to the schematic diagram. All right, so means the answer for this, okay, is not just one answer. Okay, there are more than one answer. Okay, so now we can take a break. After the break, then I will continue with the next few examples. There are a few more examples. I just check your attendance. Okay, all of you, you have submitted your form. Okay, just that one student, Go Kian Sing. Okay, I didn't see you here. Okay, who knows what happened? Okay, he joined the class just now, and after that, now I didn't see him. If he leave early, then he must give a reason. Okay, if without any reason, then I will not update his attendance, even though he has submitted his form. Okay, now I will continue with the class. Okay, the examples. Okay, the next examples is also about drawing the ULIF path using the schematic diagram given. Yeah, after we draw the schematic diagram, if we need to draw it based on the Boolean functions, then we have to draw the schematic diagram only we can determine the ULIF path. Okay, so in these examples, this stick diagram is given. Okay, so we can start to draw the ULIF path. Okay, so for this one, okay, to start to draw the ULIF path, we need to draw the nodes. Okay, okay, and the nodes here, okay, is this one. Okay, to determine the ULIF path, okay, the ULIF path has already given, okay, B, A, C, E, D. Okay, so we can use this ULIF path to draw the stick diagram. Okay, based on the ULIF path given here, we can verify it. Okay, uh, B, A, C, D, D, C, E, D. Okay, and then B, A, C, E, D. Okay, and there is also other possibility. Okay, we can get others ULIF path. Okay, not only just this ULIF path. Okay, others we can get like A, A, B, A, B, D, E, C. Okay, this one also A, B, D, E, C. Okay, sorry. So this is not allowed. Okay, this unique path is uh, is incorrect. Okay, we cannot use this because in pull down network here, it is not one directions because A, B, D, E, C. So this is not allowed. Okay, so I choose the wrong unique path, so this is not allowed. Okay, but if we try some more, we can get another one. We can get another unique path as well, not only just this one. Okay, so now since this already given, and then with the stick diagram, okay, so now we just refer to this stick diagram with the unique path given. So the order of the polylines here is B, A, C, E, D, which is based on this unique path. Okay, and then after we determine the order of the polysilicon line, then we can start to draw the connections. Okay, so this is the stick diagram with the contact at the and the metal layer and the polysilicon layer. Okay, so for these connections, again, you can understand it easily. Okay, but by labeling the source and drain terminal. Okay, so this is the source. Okay, so this is the source. We can directly identify this as a source because the contact here is connected to the VCC. Okay, here label as VCC, so this one also have to change to VCC. Okay, but sometimes we always label it as VDD. Okay, this is VCC. I just follow the one that is in the stick diagram. Okay, or VDD. Okay, this one is drain. Okay, this is source, this is drain. Okay, and this is source, this is drain. Okay, okay, to recheck. Okay, this is the transistor with input C. This is drain. Drain is connected to the source. Okay, source terminals of the transistor with input A. So this is the source terminal. And drain is connected to the output F. Okay, uh, another terminal is also a drain terminal. So this one is the drain terminal. This one is the source terminal. Okay, so these source terminals, they are in connections with the source and drain terminals of the transistor A and C, and then the drain terminals of the transistor D. Okay, means that this is the drain terminals and these are the connections for these connections in gray color. Okay, and then for the pull down networks, the source terminals for BDE transistor are connected to the ground. Okay, so here, this is the source terminal. This is drain, source, drain. This is also drain. Okay, so with the labeling of the source and drain terminals, then we can easily draw the connections. Okay, the connections that use the metal layer to make the connections. Okay, so this stick diagram is also not difficult to understand. Okay, then now I will go to the next examples. Okay, this is also another examples that asked to draw the schematic diagram and then the stick diagram. Okay, so this Boolean function is given. Okay, based on the Boolean functions, then we can easily draw out the stick diagram. Okay, not stick diagram, the schematic diagram. Okay, the schematic diagram, sometimes we call it as a transistors level schematic diagram. Okay, this means that the schematic diagram must be drawn with the NMOS and PMOS. Okay, so for this one, okay, you also can try yourself there. Okay, if you want to test your understanding, you can actually try it yourself. Okay, in your tutorial, okay, there are many questions on this topic. So please make sure that you understand and you can solve it yourself. Okay, you will need to uh, know this because it will help you. Okay, it will help you to score mark. Okay, this topic is not difficult. You just need to get to understand, and then it will help you to score mark. Okay, in your final exam. Then also it can help you to write your report. Okay, your lab report and also your assignment report. Okay, so this is the pooling functions. Okay, for the pull out network and the pull down network, it will be okay. So this one we will determines the configurations of the NMOS and PMOS. Okay, again similar. This is the AND gate. It will be series. This is O. This is parallel. This is O. Okay, then we can start to draw the diagram. Okay, the solution is already given in the next slide. Okay, but now you can actually draw it yourself before you refers to the next the solutions in the next slide. Okay, here I draft. Okay, I draft based on what is uh, writing here. Okay, what is written here. Okay, so this one will be parallel. Okay, if you are able to draw out without referring to the solutions, means that you understand. Okay, means that you understand. Okay, so this one is A, B, C, D. This is C and D. Okay, so it should be like this. Now I show the solution. So this is the solution. Okay, the solutions here is the input up network A and B are in series and C and D is in series. And then this one, in pull-down network, A and B is in parallel, and then D and C is in parallel. Both A and B and D and C is in series. Okay, they are in series. This is how we should draw. After we draw this, then we need to determine the unit path in order to draw the stick diagram. Okay, so this is the stick diagram, A, B, C, and D. Okay, the unit path here, I will not show you because I will just leave it to you to find out. Okay, because here A, B, C, and D already given. So it means that the unit path is A, B, C, D. Okay, unit path is A, B, C, D. And then they can also have another unit path like B, A, this is what D, B, A, D, C. Okay, so B, so you need to find out, okay, whether this B, A, D, C is valid or not. Okay, but you need to check. Okay, if you have time to do the revision, then you can check this whether this unit path is valid or not. You need to check. Okay, okay, but since the stick diagram has already given the order of the polysilicon line A, B, C, D. So it means that the unit path is A, B, C, D. Okay. So this one I will not explain further because I will assume that you already understand how to get this. Okay, now I goes to the next example. Okay, this is another examples also to draw the transistor level schematic diagram and then the stick diagram. Okay, except that the Boolean function is not given in this example. Okay, we have to determine the Boolean functions based on the statements given in the question here. Okay, in the examples here, a 3-input majority gate returns a true output if at least 2 of the input are true. A minority gate is its complement. Design a 3-input CMOS minority gate using a single stage of logic. Okay, so here the questions state that there are 3 input, okay, 3 input and then 1 output. Okay, the output will return true if at least 2 input are true. Okay, to determine the Boolean functions, we need to use a truth table. Okay, we need to use a truth table, and then from the truth tables, then we can derive the Boolean functions. Okay, the solutions here is given. Okay, the truth table, this is the truth table with the input, 3 input A, B, C. Okay, and Y is the output. Okay, so according to the questions, the output will return true, means it will give a 1 when at least 2 input are true. So it means that now you see this row, okay, B and C is true. They both of these are true. Okay, so it return true at the output. Okay, and then this one also, 2 input are true. Okay, 2 input are true, so output is true. Okay, and then this is uh, where the, okay, this is this row, it has a 3 input that return true. Okay, so now this output is also true. Okay, so based on this truth table, then we can take 4 of this row, okay, to determine the Boolean function. Okay, so this is the Boolean function. Okay, the y equals to a bar b c. A bar b c means this one. This is A bar B C. Okay, and this is A B bar C. This is A B C bar, and this is A B C. Okay, so these four terms is actually this one. Okay, after that we can apply some mathematics law and theorem. Okay, we can simplify it to get this. Y equals to A product with B and O with C, and then O with the product of B and C. Okay, so this is the Boolean functions that we should use to draw the transistor level schematic diagram. Okay, the diagram here, this is the diagram, okay, represent this Boolean function, the operations of this function. Okay, you also can try it yourself, okay, to draw this. Okay, to verify whether this diagram is with correct configurations or not, we can actually directly verify it. Okay, so B and C, this is the AND operations. AND operations mean they are in series. Is it in series? This is O operation, not O, this is AND operations. AND operations means this is in series. This one is O. Okay, so we can check. Okay, sometimes the solutions given is not correct. Okay, we need to double check to see whether the solutions given is correct or not. Okay, so B and C is in series, but this is in parallel. Okay, this is in parallel. Okay, and then B and C should be in parallel with this. Okay, so these solutions, the diagram here given in the solutions is not correct. Okay, they are the balik. Okay, this one should be the pull down network. This one should be the pull up network. Okay. Okay, when you do revisions, please make sure you get the correct answer. Okay, this answer, the diagram here, is not quite correct because the pull up and pull down network, they are reversed. The configurations here are reversed. Okay, this is the stick diagram for the previous one, the schematic diagram. Okay, these stick diagrams look a bit different with the one that I uh, taught you, okay, to draw. Okay, usually we draw a line, but this is not line. This is instead it use the layers. Okay, and also the input here, as you see that um, the input what I mean is the layers, the polysilicon line that use here. Okay, they are using back the same polyline. Okay, like this one, you see that B, this is a B polysilicon line. Okay, they are drawn in this way. Okay, mean that means this is mean this line this layer is B. Okay, and this is A. Okay, we also can draw it in this way. C, B, A, B, A. Okay, we also can draw it in this way. Okay, this stick diagram, this polysilicon line for A and B. Okay, they are reused back using the same poly line for A and B here. Okay, if I refers to this schematic diagram, you see this. There are 5 transistors. The 2 transistors are having the same input with another 2 transistors. So that's why you see in the stick diagram here, there is a repeat A and B here. Okay, this stick diagram, C and B. Oh yeah, it's yes, it's C and B. Okay, okay. So just now I mentioned B and A. Okay, so I'm wrong. Okay, so this is C. This is B. This is C. Okay. This is B and C. Okay, so the connections here, you also can try to identify yourself. Okay, um, this a stick diagram. Let me check again whether this stick diagram is based on the schematic diagram that is given. Okay, this is source, drain, source. Since this one is reverse, okay, this A and B, this is the source terminal. It should be connected to VDD. Okay, this is the pull out network. This is drain. This is not drain, this is source. Okay, so the drain here for B and C are connected to output. Okay, so it will be this one. The drain terminals for B and C. Okay, connected to output Y. Okay, and other connections here, okay, they are connected together at this node. Okay. Okay, so the stick diagram is correct. Okay. You can draw it with another ULI path. Okay, another ULI path can be a BCABC. Okay, this one is valid. Okay, you can use this as well. Okay, and then you can redraw it. Not redraw. You can draw using this ULI path. Okay, and then if you don't want to draw it in this way, okay, you can draw it in this way. Okay, also accepted. Okay, but if you are able to draw it in this way, then that will be good. Okay, it shows that you understand well. Okay, now I goes to the next slide. Okay, this is the another more examples of the stick diagram. The stick diagram here is a little bit different than the stick diagram that I showed you just now. Okay, as you see that uh, this is the stick diagram. Okay, this is the layout and this is the schematic diagram. Okay, stick diagram, some stick diagram looks different, okay, than the ones that I show you. Uh, which is this one. Okay, this is one of the method that we can draw the stick diagram. This is another one, and there are a few more examples that also can be drawn uh, as a stick diagram. Okay, this one is another one. Okay, you see the difference here. Okay, refer to this stick diagram. This is the metal layer. Okay, this is the polyline. This is the diffusions area. This is diffusions area. Okay, this line means this line. Okay, this one means this one. This is the metal layer. Okay, mean this one. Okay, and also another metal layers that is used to connect to the ground. So this is also another metal layer. Okay, uh, the stick diagram also can draw like this, and then using this stick diagram, we can directly draw out the layout like this. Okay, this layout is similar to the ones that you can observe using a 3D viewer in electrics. Okay, another more examples here. This is another examples of stick diagram. Okay, this one you see that this is also there is a VDD is connected by the metal layer, and then polysilicon line. Okay, also draw in a red color line. Okay, and then the diffusions area is drawn in green color, and the diffusions area for the NMOS, not NMOS, is PMOS. Okay, is drawn in this gray. This is not gray color. This is in black color. Okay, so this is another representations of a stick diagram drawing. Okay, but in your lab report, I will expect that you draw in this way. Okay, draw this way. Okay, you can just draw in this way if you are more familiar with this way. Okay, I have added a few slides here. Okay, the examples of the stick diagram I have added last night. Okay, you will find that is a bit there is uh, the slides you did not get. Okay, it is not in your notes if you have previously downloaded from Google Classroom. Okay, the slides I have updated, okay, in the lecture notes, and then I just uploaded it in this morning. Okay, you can find this slide in the newly uploaded notes. Okay, so this one is also another examples of a stick diagram. Okay, also we can draw it based on the schematic diagram. So this one is not difficult to understand, so I will leave it to you to study. Okay, this topic is about the steps, okay, of how to translate the stick diagram from the schematic diagram, and then after the stick diagram we can actually determine the layout. Okay, so this slide shows the design procedures from the logic circuit to the CMOS layout. Okay, so this is an example of a full adder. Okay, a block diagram with given the Boolean functions. Okay, we can actually draw this block diagram using the logic gate. Okay, this schematic diagram with all the logic gates. We call it as a gate level schematic. Okay, we can call this as a gate level schematic, and then this schematic we can translate it or we can redraw it in another schematic form. Okay, that is a transistor level schematic. Okay, you see all these are transistors. Okay, they are NMOS and PMOS transistors. So we call this as a transistor level schematic. Okay, and then after we draw this, then we can use this drawing, the schematic drawing, to draw the layout. Okay, so all the processes here, the drawing, you are actually learning. Okay, you are learning in your lab. Okay, so as a summary, VLSI design aims to translate circuit concept onto silicon. Okay, the stick diagrams are a means of capturing the topography and layers informations using simple diagram through color codes. Stick diagrams helps to plan the layout and routing. It acts as an interface between the symbolic circuit and the actual layout. Okay, so this is the end of the chapter 3. Okay, so any questions there? Okay, uh, you're asking about the slide 55. How to get a bar in slide 55. Okay, you mean this bar, right? This bar. Okay, this bar, originally it is given. Okay, if it is not given, then you will have to uh, you will have to make it a bar. Okay, if you have to make it a bar, okay, last time I have shown you all before. Okay, so for this one,
Miss, you're not sharing your screen.
okay, okay, so now you can see my screen. I just share. Okay, you are saying this bar, right?
Yes.
Okay, so this bar, the questions here give these functions with a bar. Okay, so it comes with a bar. So this bar to indicate that this function is for the PMOS. Okay, initially, okay, this function is actually means y equals to a, b plus c plus c, b and c. Okay, a bar here means that uh, the functions here all will be how to say, okay, these functions will be inverted. Okay, will be inverted to get the output. Okay, no, let me think how to explain it properly. Okay, just now I say it not clear. Okay, so okay, for this one I mentioned before, this is for the pull up network, right? Pull up network consists of the PMOS. Okay, the PMOS operate, okay, based on the input. Okay, the input when it is low, then the PMOS will be on. Okay, so all these AB's, AB is the input variable. Okay, they are actually input, and any input is low, means that A bar, A, any input is low, it will give output. Okay, it will on the PMOS and then it will change the output. Okay, so this one, the bar here indicate the behavior of the PMOS. Okay, uh, this is how I can explain why there is a bar and how to get the bar. uh, this bar is already original is here. Okay, original is given with the Boolean functions, so you need to use these functions to draw out the pull up network. Okay, for pull down network, this is another functions. Okay, this functions is for the pull down network. You see there is a bar. Okay, here the input variables A, B, C, they are no bar because the NMOS, the transistor is switched on when the input is high. Okay, so there is no bar. Instead, this is Y bar because this is output. Output will change if any of the transistors of NMOS change. Okay, this is how we should understand it. Okay, others examples, if given like this, a and y equals to a, b, c. Okay, these examples, if without the bar, we need to find out the one that is with the bar. How to find out? Okay, we have to apply some the theorem, the De Morgan's law. Okay, that is y equals to double bar a, b, c plus bc. Okay, I explained this before. Okay, this one we will be able to get something like this. A, this is A bar plus B bar okay, something like this after we apply the De Morgan's law. So using this one, only we can start to draw the pull up and pull down network. Okay, we need to use this to find out the Boolean functions for the pull down network. Okay, A bar. Okay, so this one is for the pull down network. We need to determine this first if the Boolean functions has no bar. Okay, we need to determine the one that is with the bar, and then we use this to get the Boolean functions for the pull down network. Using this one, then you will get to draw the right diagram. Okay, with the right configuration. Okay, so this is the explanation. Okay, I have a few things that I want to tell you. Okay, before we end the class today for lecture. Okay, next week. Next week, some of you will be going back to campus, right, to have class face to face. Okay, I want to know how many of you will go back to campus? Okay, maybe now it's hard to say and hard to determine how many of you. But for those who will be going back to campus, I hope that you already get your booster. Okay, I will need to check your Sejahtera. Okay, my Sejahtera, you need to show me your My Sejahtera. Okay, next Monday, during face-to-face class. Okay, next Monday, face-to-face class is my first class in campus. Okay, I am not sure whether the class can be conducted smoothly, but I will ensure that the system is set up well to do both face-to-face class and then the online class. Okay, I will use back the same method. Okay, I will write through screen. Okay, not on the whiteboard. Okay, and then I also um, use back the same method. Okay, I will use back the same method to teach. Okay, because this will actually help me to save the time. Okay, while I'm teaching. Okay, I will not write in the whiteboard. I will using the same way, except that some of you will be sitting in the classroom. Okay, in TAUC. Okay, so for those who will attend class, I will expect that less than 10 students. Okay, you will have to show me your My Sejahtera that you have already fully vaccinated. Okay, and also vaccinated with the booster. Okay, and also please make sure that you be careful when you come to campus. Okay, and then okay, next Wednesday, we will be having lectures and practical. Okay, lecture class I will cancel because I have an interview. Okay, I have an interview at 2:30. So I have to cancel the class, the lecture class. Okay, I will be able to make it within 2 hours. So that means that a practical class, I can still continue with the practical class. Okay, means that only lecture class will be cancelled, but but practical class will be on. Okay, practical class will be on, but lecture class will be cancelled next Wednesday. Okay, so I hope you are clear. Okay, later I will announce it again in the Google Classroom. Okay, so that is to remind you. Okay, I hope there is no issue with that. Okay, let me see anything else. Okay, we will be having another practical class today for group 2. Okay, so later group 2 students please stay back. Okay, and then about your attendance. Okay, let me see anyone. Okay, so just now I already checked. All have already filled up the form, and then Go Kian Sing is here now. Okay, so we can dismiss class now. Thank you.